You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Chris Smith, welcome back.
Good morning, Chris.
I'm the frozen vodka guy, in case you've forgotten.
No, I was saying to Thomas just now, Chris is back.
And it's the easiest
Chris
names.
and Chris, it was that confusing day where everyone's called Chris.
Exactly. But I never forget people called Chris because I always remember their names, right? I remember other people's names, but Chris is I can cope with. Now, I believe you're going to tell us about something called a Rosetta mission, which is about sending a Rosetta pizza into space or something like that. Is that what it's about?
Well, it's a pretty big day today because the Rosetta mission comes to an end. The probe Rosetta launched in 2004, and it's made a journey of about 500 million miles, 500 million kilometres. We should get it right, shouldn't we? Across the solar system to unite about a year ago. It's 2 years ago, November 2014, with the comet 67P Churyumov-Gerasimenko. And the Rosetta probe then deployed the Philae lander, which you might remember, this had a slightly catastrophic landing because it bounced a few times before coming to rest on the comet's surface. But this was an amazing achievement for the European Space Agency, who spearheaded, funded and supported this mission. And it was the first time anyone had ever done anything like that. The Rosetta probe has continued alongside orbiting this comet, which is zipping through space at thousands of kilometres an hour. And it's taken pictures and it's given us the insights that we never had into the structure of these comets. But the comet neared the sun last August and has now begun on its outbound leg again now. So it's heading towards the reaches of space out near Jupiter again now. And it's going to get cold and dark, and there won't be enough power to run the Rosetta probe anymore, which is dependent on solar energy to run itself. And so the European Space Agency have made the decision to touch down, effectively crash land the Rosetta probe onto the surface of the comet near to its Philae lander baby. So mother and daughter can be reunited, and the idea is it will just sit there for the rest of its time now, but they'll get some really spectacular pictures going in as it goes in on the final touchdown approach. That will happen in about 2 hours time, so it's manoeuvred into the position and it's going to be beginning to get close to the comet now, and it should just crash down at roughly fast walking pace sort of speed later in about 2 hours time.
As you say, it sounds really spectacular. I mean, are people, ordinary people, going to be able to see footage of this at some point? I mean, are there cameras?
Well, there's a between 20 and 40 minute time lag to get the signals back, because it's a long way away. And there's also a little bit of uncertainty in exactly what the sequence is going to be, what the timings are going to be, and when it's actually going to crash land. But it will be sending back data because it has line of sight to us right up until the last moment as it smashes into the surface. So we will almost certainly get some pretty interesting pictures, because the area they have chosen for it to come down on is right next door to a number of features which have been spotted on the pictures that it's been sending back. So scientists have been poring over the images of the surface of this duck-shaped comet, and they have highlighted various regions of interest, and they've chosen one which looks like a promising place to go in to get the benefit of some close-up images. The ESA, the European Space Agency, are really good about getting the pictures and all that kind of thing out. And when they did the initial landing, they actually had a live web stream of all this. So there will be lots of online content that people can plug into in a couple of hours' time.
So where should they be looking? I mean, is it the European Space Commission, NASA? Which sort of website should people be looking
this is a European Space Agency mission. And so if you look up ESA, European Space Agency, you can see and type Rosetta, ROSETTA, into your web browser. You will find all the links that you need. There's also a really comprehensive FAQ section which gives you all of the mission stats and parameters, what's happened, what it's found so far, what it's going to do next, why they're doing this, and there are links there obviously to the other resources that are going to be trickling out. And I think there's going to be a lot of press around this tomorrow too, so if you miss it online, it'll definitely be in the news and in the other news tomorrow.
Let me ask you one FAQ before we bring in a couple of listeners. They're calling us on 011-883-0702 and 021-446-0567. Chris, what difference does this make to life on Earth, poverty, relief? I mean, I know this is a kind of real anti-nerd question, but what can ordinary people take out of this sort of space exploration?
Well, there's a number of things to consider. One is that where we all came from, how our planet formed, and how it happened in the first place are pretty big questions, which you have to ask yourself, what's the point of humanity and having the ability and the brain we have if we don't use it to answer hard questions? So that's the academic answer. The more practical, what does this mean to the man and woman in the street here on Earth answer is, if we did not push the boundaries, if we did not invest in these sorts of missions, which are spectacularly expensive, granted, but because they force us to push the envelope so hard, they force original thinking, they force original engineering, and they create tangible, tractable edge and end benefits for people on Earth. In other words, the technologies that we need to develop and the problems we need to solve in order to make these sorts of missions possible have spin-offs here on Earth. And a really good example of that is anyone who is using Wi-Fi right now, and there are thousands of people right now listening to this program who are on Wi-Fi. If radio astronomy, sort of searching deep into the reaches of the universe, had not been invented then and wasn't pursued, they would have had no reason to invent Wi-Fi, which we're all now using. So there's one very simple example. If we weren't smashing particles together at CERN to interrogate the fabric of the universe and the structure of atoms, then we wouldn't have the internet. And if we weren't doing that and generating enormous amounts of data, then we wouldn't be under pressure to try to work out original ways to store and compress data, which is what scientists have also done. So there are lots and lots of spin-offs. If you invest big and think big, you then have tangible end benefits for everybody.
Great. Chris in Randburg, you want to ask a question about the planets. Welcome to the
Another
show.
Chris.
Good morning, Chris. Good morning, Chris. And
Hello,
I don't
Chris.
know whether it's unique. There are 3 Chris's on the radio simultaneously.
It's called a threesome, Chris.
And I am genuinely a Chris, I promise. Okay, on the subject of all these space shots, the pictures we get of the distant planets are extremely clear and bright and spectacular. But let's just take the pictures of Jupiter. It's extremely far from the sun, so it's very, very dark out there. How do they get the pictures so bright? I can think of several ways, but I don't know if any of them is correct. Because, you say, it's not only is it dark, but the spacecraft is moving at hundreds of thousands of kilometers per hour, so they can't take time shots. And anyway, is there an explanation for it, Chris?
Hello, Chris. Well, the answer is that here on Earth we have a problem taking decent photos of things in space because we have an atmosphere in the way. In space, you have no atmosphere, so you can get clearer, sharper pictures just for that reason. And although the spacecraft is moving, it's moving in a predictable, smooth way because it's not being jostled around by air currents and things like that. So actually making sure you get a nice, sharp picture because you can do long exposures is relatively easy in space. So those are the 2 main ways of doing it. Number 1, you have no atmosphere or other particles in the way to mess up your image. Number 2, you spend a lot of money and have a very good camera to start with, which helps. And number 3, you can do nice long exposures because you have a relatively smooth trajectory and you can get good contrast that way in order to make the most use of the light that there is.
Are you happy, Chris? Makes sense?
Image enhancement once you get the picture back if necessary.
Absolutely. That's the other thing you can do, of course, which is even if you capture a low light picture, if you have a sensitive enough sensor in your camera, then it's the difference between the signals and you can then enhance them and pep them up and make everything brighter. The killer is if you overexpose your picture in the first place because then you've thrown away data and there's nothing you can do about that.
Well, thank you, Chris. Nice talking to you.
Thank you, Chris.
Thank you, Chris. So this is a Chris Mutual Appreciation Society. Zuki in Cape Town, you also want to talk about light and darkness. Welcome to the show.
Hi, Chris, and hi to the other Chris as well.
Hi, Zuki.
Yes, I don't know if maybe it's my imagination, but it looks like when you see street lights from afar, like if you see a city from afar or if you see it from the air, the street lights appear to be blinking. Do you know why this is?
Well, there's a number of reasons, but it's the same reason probably that stars appear to be twinkling in the night sky. If you look up at a nice starscape in the sky, you'll see the stars appear to not be a uniform brightness. They appear to be becoming a little bit dimmer and a little bit brighter. The reason for this is atmospheric aberrations. We were just talking to Chris, who phoned in, Chris, about taking photos in space, and I pointed out that we don't have very good views of the night sky because we have an atmosphere in the way, and that the best pictures taken from space case of things like the Hubble Space Telescope, where you're outside the atmosphere. The reason for this is that when you have an atmosphere, the atmosphere has areas of warm air and areas of colder air. And when light goes from an area of warm air into colder air, the density of warmer air is different to the density of colder air. And this means that the speed of light in those different patches of air is different, because the light does travel at a different speed according to the density of the medium in which it is passing. So if you have patches of warm air and colder air between you and the thing you're looking at, the light that goes between your eye and the object you're looking at is going to have bent and twisted, because it will have changed speed along its journey to you. And that changing in speed bends the light and makes it wiggle. And this makes the light appear to wobble backwards and forwards, and will also therefore affect its intensity, because the amount of light that's coming into a certain area at the back of your eye will get bigger and smaller, making it look as though it's getting brighter and dimmer. But it's actually just the light wobbling as it comes through patches of different density air.
702 and Cape Talk.
The Naked Scientist.
Welcome back. My name is Chris Vick. It's 21 minutes past 10. We're talking to Dr. Chris Smith, a.k.a. The Naked Scientist. Yaku in Benoni, welcome to the show.
Hi, how's it going?
Did I pronounce your name right?
Chris.
I'm sorry.
Yes, it's Yaku.
Yaku, great. Go ahead.
Hi, Chris. I've just got a quick question regarding black holes and Hawking radiation. How does radiation escape from a black hole if a black hole is able to ingest everything that comes in its path, including light? Does that radiation come from within the black hole, or does it come from outside the event horizon? And just a follow-up question, do black holes ever diminish, or do they continually grow forever?
Hello, a lot of questions there. The answer is that black holes don't exist forever, and they do give away material, this Hawking radiation, and this means that over a very, very, very long time scales they will evaporate and disappear. But actually, on the time scale that we're looking at them, no, they're just there. Now, why would a black hole be able to give away radiation if things can't get out of a black hole? Because the reason it's black is because it is so dense, it's so gravitationally active, that it prevents even light from escaping. How does it do that? It does that because the black hole deforms space-time and curves the fabric of space in on itself, so that even light coming through is pulled in. So how on earth can anything get away? Well, the answer is the intense gravitational field around a black hole will lead to the acceleration of particles around the black hole. So if you have a black hole which is drawing in material, things are going to be orbiting that black hole, and they're going to accelerate, and they're going to accelerate more as they get in towards the black hole. And if you move or you accelerate a charged particle, then it will feel a force, but it will also emit energy. And in exactly the same way, we have particle accelerators on the Earth, for example. A synchrotron is a good example. If you accelerate electrons and you make them move in a ring, because you're accelerating the electrons along a curved path, that means that they are continuously moving, and if they're continuously moving around a curved path, they are going to emit radiation, and that's where the X-rays come from in a synchrotron. It's the same around a black hole, that the particles which are orbiting and accelerating as they move towards the black hole event horizon will therefore emit radiation like X-rays, like gamma rays, and in some cases light spectrum that we can't see, but it's there. And if you look with the right wavelengths of cameras, you can actually see this radiation coming off. And so that's why it's not the particles getting into the black hole and then spitting stuff out. A lot of this radiation that you can see is stuff being cooked on its way into the black hole because it's being accelerated, and when you accelerate charged particles, they give out radiation.
Fascinating. Thank you, Chris. Let's bring in Udinans from Cape Town.
Hello.
Hello. Did I pronounce your name correctly, Udinans?
Yeah, you Udinans. That's right.
Welcome to the show.
Can I ask my questions?
Please go ahead.
Hello, Doc. You can tell him my wife is suffering for loss of smell and taste for the last 6 months, and we've been to 2 specialists, and they say you've just got to wait. I just want to know what is his take on it. Loss of smell and taste.
Well, first of all, most people don't realise that what we call taste is largely all smell. Because when you put food and drink into your mouth, what actually happens is, although there will be direct stimulation of the nerves in your mouth, which will tell you how hot something is, whether it's spicy or not, and will pick up a limited repertoire of tastes, and these include bitter, sweet, sour, salty, umami, the meaty flavour, for example, most of what we call taste is actually volatile molecules which, in the nice warm environment of your mouth, vaporize, go to the back of your nose, and then bind onto what we call the olfactory epithelium. There is a patch of tissue at the top of your nose where there are sprays of nerve endings coming through, and those nerve endings have chemical receptors on them which can pick out the presence of different volatile molecules that you breathe in or which come from your mouth. The combination of those receptors that get activated by different odorants or chemicals in the air or in what you're eating stimulate different repertoires or assemblages of these nerve cells, which sends that united signal to the brain, and the brain then decodes that as taste. So if you damage your smell pathway, or if you have a problem with the smell pathway, one consequence is also you tend to describe this as, well, the most obvious manifestation is I can't taste anything because you're limited down to just the suite of receptors in your mouth, which are just things like salty, sweet, bitter, and that kind of thing. So if you have an abrupt, sudden loss of the sense of smell, this can occur for a number of reasons, and taste. It usually is because of a viral infection or a cold, which can damage or clog up the nasal passages and stop the smell and taste things getting onto the olfactory epithelium. Also, head injuries can do this, or other infections which affect the brain. It's very important, if this is something abrupt that came out of nowhere, no obvious reason for it to happen, and it's persisted, it's important that that's properly investigated.
Udinance, does that help you?
Thank you very much.
Thank you very much for the call. Alton in Pretoria, you sound like you have a very complicated question. Alton? Lost him. Amanda, Centurion? I like your question. Let's go.
Okay, hello, Double Chris. Good morning
Hi.
to you guys.
Hello.
Okay, I'd like to find out, why do our tummy, when we are hungry, why does it rumble? Why does it make rumbling sounds? What causes it to sound like that?
Well, the posh word that medical people use to describe a rumbly tummy is borborygmi. So there's word of the day, borborygmi, which means a rumbling stomach. The reason your stomach rumbles is because we develop a bowel habit. There are lots and lots of nerve cells. In fact, some people say more nerve cells in your intestines than there are in your brain. That's certainly true in some people I know's case. But the point is that you have these nerve pathways in your gut and you learn a pattern of behaviour. Your intestines know, based on your regular pattern of activity, when you tend to eat and when you tend to sleep. And the cycle, therefore, means that there's an expectation on the part of your intestines of being fed at a certain time. And so the intestines begin to gear up in order to digest your dinner. This includes increasing muscle activity. It includes increasing the secretion of gastric juices, which are acids and enzymes that break down food. At the same time, superimposed on that is that your brain also knows when you tend to eat, when you tend to sleep, and therefore when you're going to need energy. So your brain also sends signals via your vagus nerve down into your intestinal system to turn it on in anticipation of eating. Because part of the success story of the human and animal system is not just reacting to things, it's being proactive about things. Getting your body ready to do what's going to happen to it is key to our success. And so the body gears itself up expecting a meal. And when you don't eat, then it's sitting there with nothing to do but all these juices sloshing around and the muscles working overtime, and they start squeezing things backwards and forwards, waiting for food to arrive. And it makes those sounds because there's no food to soak up the vibrations. When you then eat, you A, feel better, but B, there's stuff there so that it soaks up the sounds and it doesn't sound quite so bad.
Amanda, go and have something to eat.
And one more question.
Can you make it about 5 seconds? Sorry, we got the news coming up.
Okay, I just wanted to know, more personal, how come Chris knows everything? Medical, sciences, is he a doctor, is he a scientist?
All Chris's know everything, Amanda. All Chris's too, not just this one. Thank you very much for the call, we appreciate it. Dr. Chris Smith, thank you. You do know everything.
It's been a pleasure. Thank you, Chris.
I'm very impressed. Thank you very much for that.
I think, actually,
Just say that again. Thomas cut you in half.
I think she was talking to you, actually, Chris.
It was you. I just busted. You're the clever one. I can spin. I can't think.
Good to talk to you.
Thanks very much, Chris.
See you soon.
Great. Take it easy.